Assalamu alaikum, Bismillahirrahmanirrahim. Today we will start our 10th week lecture number 19. So in the previous lecture we have done we started heat transfer and also learned the Faraday law of heat conduction. This formula Q dot is equal to Ka dt minus dt upon dx. Okay, and we also learned the different material, the different phases of the substance, how the conduction properties in different phases, like in gases, like in liquid and then solid, how it is changing with respect to time, with respect to temperature. So in the gases, the conduction, the thermal conductivity, the universal property of the material is increasing in the gases and has a turnover trend in the liquids, and in some solid it is has an increasing trend, and some solid that is mostly used as a conductor, mostly metals, they have slightly decreasing trend. Okay, anyway, we also learned the thermal diffusivity. As long the higher the thermal diffusivity, higher the heat transfer rate will be occur, and lower the thermal diffusivity correspond to the lower heat transfer rate. Okay, it is just a ratio of heat conducted divided by heat stored. Okay, so the non-conductors like wood, beef, they stored energy, they stored heat energy, so that why the alpha value will be lower and they less heat conducted. Oppositely, the silver, gold, copper has an opposite property, they conduct more heat and stored less, so the alpha value of these metals are greater. Anyway, we also done the numerical. We also calculate the heat loss occur in the home due to the winter season. The internal temperature of the house is maintained by the electrical resistance heater that maintain at 15 degrees centigrade, but outer temperature is 4 degrees, so it loses the heat. And how much the heat is losing over here from the conduction of this concrete roof is around 169 watt, and the energy corresponding to this heat energy is like 16.9 kilowatt hour, that is a unit. So if we multiply with this units, with respect to unit price, like in Pakistan the unit price is 17, so we take it as a 17, but in the question it is some like $0.08. So it costs like 287.3 rupees per day. Okay, anyway, so we start the topic of this lecture from this slide. We have a different in basically what are the application of conduction in your particular field is to related to the insulations, because we apply insulation in the construction material, in construction, like construction of buildings, homes, to avoid heat trap inside the room, or in winter to avoid heat loss out from inside to outside of the room, just like we have done in the one numerical. Okay, so these are the properties these are the levels of thermal conductivity with respect to different material. Like in gases the thermal conductivity is lower than we get in the insulations. In insulation we have liquid, we have gases. We also apply some layer of gas between, or air between, to have a good to have a insulation, like air, mostly in the bricks in other countries the bricks are made in which there will be the air gap, and due to the air gap it resists the heat loss from inside to outside, or resists the outside temperature in to the inside room. So air is also a good insulator. We provide air as an insulator in between two different layer of the material. And further we to avoid gaps, we apply some of insulation material like fibers, wood, foams, etc. So we are interested in this part. These are the related to the higher conductivity means the higher heat transfer rate. and it is related to the electronics, electrical engineering, in which they need to cool down their circuits, etc. So they are interested on these parts, like in liquid cooling, like in power generation, we have to lower the temperature of the engine, like in car, in motorcycle. So we used radiator, and in the radiator there was a water water transfer heat from engine to the outside environment. So we'll use also a liquid part to conduct heat, and then after that we have a solid portion like non-metallic solid, oxides, rocks, foods, rubber, metal alloys. They have a very good thermal conductivity. They conduct electricity as well as heat. Then pure metals, then non-metal crystals like diamond, graphite, they also conduct heat. Okay, we discuss this insulation part later with the numerical, when we done all the conduction, convection, and radiation part. So we we solve the numerical as a whole, because in every single moment there's not only one heat loss. All of the heat losses are coming, or is experiencing in the practical world, whether you are talking about the power generation, whether you are talking about the homes. So whether you're talking about the human being also radiate, give radiations, heat radiations, conduction, convection. So all together, when we done all the part of the conduction, convection, radiation, so we study then we will study with the especially related to your field, insulation in the homes, how we can calculate the what should be the insulation required in the in construction any material in any building, etc. But for an instance, I just get the slide of the most used insulation in Pakistan. We have different insulation material in the construction industry. Fiberglass, that has a resistance value. Later we will study the resistance. Right now, just you need to know it is the opposite of thermal conductivity. Higher the resistance value, it will resist the heat. it will it will not conduct heat, or it will lower it has a lower heat transfer rate. So fiberglass has a R value 3.1, polyethylene insulation 6.3, then polystyrene insulation, then rock wools. These are the some common metals insulation used in construction material. Okay, and their application: walls and ceiling, roof, wall and ceiling, attic insulations, rock wool. There's positive parts, there are negative parts, etc. We will discuss it in detail later, because it is related to your particular field. So these are the example of jumbalone boards. Basically, it is available in Pakistan, and these kind of insulating material can be placed in between the walls to avoid heat transfer from sun into inside the room, like heat trapping from outside temperature or from sun to inside room. Or in winter, oppositely, the heat maintained inside the room cannot be lost to outside at lower temperature. So basically, when you will pass out from the NID University, you will be the part of any design firm, design consultancy, or in construction, or in labor part. We have a consultancy firm, and we have a contracting firm. So wherever you are, you have to know about this construction material insulation. It will reduce the operational cost of the building. Okay, so this is only example we have done. When we done all the part, we will done this kind of numerical, you will see. Okay, so I just taken the numerical, or not numerical, it's a numerical, but it's an example 1.7, and it is related to the bricks. So I just use it. I will not solve it, but it is very simple numerical. I just slide down the analysis of this bricks. First, we read out an engineer who is working. It is example 1.7. It is related to the bricks that is used in the construction material as a construction material. An engineer who is working on the heat transfer analysis of brick building in English unit needs to needs the thermal conductivity of bricks, but the only value he can find his handbook is 0.72 watt per meter degree centigrade, which is SI unit. So the who's the engineer? The English engineer. So he is more familiar with the English units like pound, inch, foot, etc. To make material to make the matter worse, engineer doesn't have the direct conversion factor between the two unit system. The thermal conductivity. Can you help him out? Yes, of course. We know that 1 watt is equal to 3.412 BTU per hour. In SS system, we have a unit watt or joules per second, but in the British system or English system, we have a unit British thermal unit, the unit of heat transfer, and divided by R, so it is BTU per hour. So it is 3.412. So, and from your calculator, you can calculate the 1 degree is equal to 1.8 Fahrenheit. So we just place this conversion factors into the whole thermal conductivity formula, and we get the answer in British system units. And 1 meter is equal to 3.2 feet. So we apply 1 watt per meter. So 1 watt is 3.412, divided by meter is 3.28, multiply by divide by degree centigrade, 1 degree is 1.8. So we apply this formulation, we get the value of thermal conductivity of brick in British units. Okay. So now we get the K value, thermal conductivity value in the British thermal unit, that is 1 watt per meter is 0.577 BTU foot Fahrenheit, and it is a we get the direct conversion of one thermal conductivity value, 1 watt per meter degree centigrade, but the thermal conductivity of brick is 0.72. So we just multiply this 1 watt per meter degree centigrade 0.17, so it becomes 0.17. So definitely when we apply this, multiply both sides with 1.17, we get the value, 0.72, we get the value of thermal conductivity of brick, that is 0.42 BTU per hour foot Fahrenheit. So I hope you will get the clear in the thermal conductivity and its formulation. Further, I will just give some homework assignment of these numericals, so you get practice of these numericals. You won't be in trouble in final examinations or in quizzes, etc. So now move towards another mode of heat transfer, that is a convection heat transfer. Convection is the mode of energy transfer between a solid surface and adjacent liquid or gas that is in motion. Okay, the combined effect of the conduction and the fluid motion is convection. The heat transfer through a liquid or gas, however, can be conduction or convection depending on the presence of any bulk fluid motion. Heat transfer through a fluid by convection in the presence of the bulk motion, and by the conduction in the absence of it. Okay, so we know that in the solid the molecules cannot move, so in the solid the bulk motion cannot be done. So the only mode of heat transfer is by the vibration of the molecules and to one to another and moves on. And in the metal we have a free electrons, so the heat transfer becomes more rapidly. But in the liquid and gases, the molecules can freely move, so it can have a bulk motion and as well as the vibrational motion. So in the convection we have a combination of heat transfer by the bulk motion and by the kinetic energy of the molecules by contacting one molecule to another. So in practical, we get the video in previous oh, I just deleted. Anyway, we just we get the diagram over here. So convection is between the solid particles, the solid body, to the liquid or gaseous molecules. Mostly the convection in this form. So, and also it can be gases to gases or liquid to liquid. So for an example, we have a hot block over here, and the air is flowing over the hot block. It takes heat from solid object to surrounding area. Here we get the velocity profile. The velocity profile of the air is like this. Assume that air is moving in this direction when the air is near to the block. So the velocity due to the contacting of air to the hot block, the velocity gets down. So so as we move above, the velocity of the air will increase, and after some position it becomes normal. Okay, but when we make the heat transfer profile, it is opposite to it, because the particle of air in the block near to the particles of air near the hot block will stay more time in the hot surface, so the heat transfer of these particles will be higher. And as we move on above, goes beyond the hot block or body, the velocity profile the temperature profile gets lower, and after some time, as the velocity becomes constant, the heat transfer also become constant. So the fluid motion enhances heat transfer, since it brings warmer and cooler chunks of fluid into the contact, initiating higher rates of conduction at a greater number of sites in the fluid. Consider cooling, as we talk about that. Consider cooling a hot block by blowing cool air over the top surface. The heat is transferred to the air layer adjacent to the block of conduction. The heat is then carried away from the surface by the convection, that is, by the combined effect conduction within the air, that is due to the random motion of the air, and the bulk or macroscopic motion of the air that remove the heated air near the surface, replaced it by the cooler air. Okay, so we can have two types of motion over here. One, if we have a force motion, like fan is blowing air over here, and even though if there will be no fan, but we have a hot block over here, so the air surrounding the hot block becomes hotter, and due to the hotter, it expand, the volume of the gas is expand, so density of the gas becomes lower. As the density becomes lower, so hot air moves above, and there is a vacuum over here when the air is moving above, so there should be some particle to fill up this gap, so cooler air comes down. So even if there will be no flow of air or any liquid, the natural convection flow will be start in convection. That is a property of convection heat transfer or mode of heat transfer. In conduction, there will be no motion in solid object, it just expand the volume, or the linear expansion, or the volumetric expansion. But in the convection, there will be natural convection, a natural convection flow can also be started. Like for an example, that is a type of convection. As I just give an example, the forced convection and free convection. The natural convection started over any surface is also called free convection. In the previous diagram, we also learned that air is blowing, so it's a forced convection. Like for an example of hot egg, if the hot egg plays over any surface and we place a fan, so we force air to blow and uh, get heated and goes out. So the heat is removing from this hot egg, and it's get cooler by the cold air. Okay, and it taken the heat from the force air of the blowing of the air. But if we stop that fan, there will be no force of flow by any external means. There also a natural convection flow is started in the convection. As tell before, that if any hot object in the surrounding or adjacent air surrounding it gets hotter, and due to the temperature increase or becomes hotter, it will expand. Gas also expand. So when the gas molecule expand, it becomes lighter. Okay, the density will becomes lower. So due to the density difference, the hot air goes above, and to get to fill the gap, the lower temperature air fills this gap, and then it also becomes hot and goes above. So a natural flow is start naturally. There will be no external motion that is pushing that air. Naturally air is moving from downward to upward. That is a natural convection flow, and we experience it in many places. Like for example, uh, you feel that you can experience that the when we place in a heater, we need to place at the bottom. I just given I have a picture of it. Okay, like this is an example of natural convection. This is the hot radiator or any stove, we place at the bottom. Why? Because in the lower surface, in the lower height of the room, we have a cold air, and higher height of the room, we have a hot air, due to the density difference. So the colder air contacted contact with the surface of this hot radiator becomes hotter and moves above, and the natural flow is start when we start this hot radiator. There will be air flow surrounding the air, and the whole temperature of the room becomes uniform. Like in fridge, you some student also asked this in the comment box, why there is a cooling plate on the top of the fridge? Just due to the natural convection. Because if we do opposite to that hot radiator, we have an example of compartment of fridge or air conditioning. So if we place need if we need to lower the temperature of the room, we have to place AC or in the fridge compartment cooling plate in the top. So the hotter air becomes colder, and the volume of the gas becomes decreased, so it becomes heavier, so naturally it moves down. So when the air from the cooling plate or from the air conditioning, the hot air becomes colder and it's moved down. And when it's moving down, it cool down anything placed over in the fridge or by contacting any human being. So the air which is having a lower temperature contact that object and becomes hotter, and again it lift to the top. So a natural convection flow started, and the whole compartment of the fridge or room becomes uniform. But if we done oppositely, if we place a cold plate in the bottom of the fridge, so the air of the fridge in the bottom area will be lower, will have a lower temperature, and it will stick to that, and hotter, and above portion of the fridge becomes hotter, and there will be no flow. So we have a difference of temperature, and anything which is kept on the top side, it has a higher temperature, and anything which is kept on the lower side, it has a lower temperature. So we don't want this in the fridge. So we place that cold plate or cooling plates in the top side of the fridge. So we have a natural convection flow, and we have a uniform temperature throughout the fridge or throughout any room. We have an example, and I have just video of it. This is the experiment which we have done in the mechanical engineering lab, in which this is a test tube and it is filled with water. We place some kind of visual thing like ink. So ink goes down and settle over here, and when we heated this and the whole water in the steady state or in the in its position, it is not moving and has zero velocity. So all the water, it is in the stable condition, or it is in the static condition. When we heat it or light the stove over here, there will be natural flow start from this side, because if we heated this plate at this point, the liquid of this point becomes heated, and it expand. Due to the expansion, its density becomes lower, so it moving upward. And when we it move upward, there will be band, so it moves like this and move like this. So this liquid move above, so this liquid take place over it, and it also move upward. So there will be natural flow started over here like this. Let's play video, and you also, we just put this ink over here. Now it settled down to the bottom. Yes, yes. Now it settled down bottom. So now you can visualize that the natural flow is start due to the heating of this bulb. You can see that the water moves upward, and if we remove this stove, there this lipid ink will settle down in the bottom. There will be no flow.
This is the type of motion that occurs when you heat near the bottom of the pan, is closest to the burner, gets the hottest, expand. So that's convection. It's motion.
You see that the flow of motion, it has a natural.
I think it's kind of pretty.
So this is basically free convection or natural convection. And another type of convection is forced convection, in which we are forcefully apply any liquid or gases over a hot surface. Like you can experience it in your laptops. In laptops there will be forced convection, because the fan, the blower inside installed in the laptop, which cool down the internal circuit of the laptop. But right now we have some small laptops, yeah, mini laptops, they don't have a blower, they don't have any fan inside it. So in that example, it loses the heat towards the surrounding area is by free convection. Okay, like laptops, like mobiles. In mobiles, the battery get heat up, so it lowered by the natural convection. You can also add some any other example related to it. Now the law related to the convection is Newton law of cooling. It is stated that the rate of convection heat transfer is to be observed, and it to be observed to be proportional to the temperature difference and the surface area. I just correct this wording. I don't know why it replaced over here. Okay, so the heat transferred in the convection by the Newton's law of cooling, or by it is just done by experiment or by physically, it is directly proportional to the area and the temperature difference. This is the temperature of solid object or a heated object, and T infinity is the temperature of surrounding area. Now you can talk about that, what temperature of at which point. Like for an example,
this is a demonstration of convection.
Yes, for this particular example, we have a hot egg. The Ts, the temperature of the Ts is the temperature of this hot egg, and T infinity is the temperature of surrounding area. Now you can ask that at which point we have to get the temperature, at which point, this point, this point, this point, this point, or this point. So we have two kind of temperature. We can differentiate in two kind of formulation. If we take in that temperature to a specific point, we call that temperature local temperature. Local temperature, like at the height of 2 centimeter, at height of 3 centimeter. So we can call them as a local heat transfer temperature, and we apply the coefficient with the local heat transfer coefficient. So Q is directly proportional to area and the temperature differential. If we remove that proportionality, we have to apply some constant. Like in the conduction, we have a thermal conductivity. In convection, we have a heat transfer coefficient, convection heat transfer coefficient, and it has the similar value like watt per meter square Kelvin. So now in this H, we need to take temperature um, in the Kelvin, but it is the difference of the temperature. So we can also take the temperature in degree centigrade. Okay. So I'm just talking about the which temperature. Ts is completely understandable, that temperature of a solid object. But what about the T infinity? T infinity is, we can relate H and T infinity with two different formulation. If we take temperature, like for this numerical, if we take temperature over here at certain point, no, we get the better. Yes, this picture represent this problem. What should be the T infinity? Okay, so if we take this, you can see that below the hot object, the surrounding air will have a higher temperature. As we move above, the temperature becomes lower, and at certain point the temperature becomes constant. So if we take this temperature T infinity, the H will be the we call it as a average T infinity, or average heat transfer temperature, average temperature. And we also take the convection heat transfer coefficient, the value of H, also average value. But if we need to take the temperature at this point, we also need to take H at this point. Okay, it is called local heat transfer coefficient, local convection heat transfer coefficient, and also temperature will be the local temperature. Okay, we used to calculate this type of a complex numerical in mechanical engineering, but right now we in your case, we mostly the hot object at some distance, and we normally take temperature T infinity, that is average temperature or uniform temperature of the room, and also take H as a common convection heat transfer coefficient, not local convection heat transfer coefficient. I just explain to avoid any difficulty or complications which you might occurs in your thoughts, that what kind of temperature or T infinity should be needed to take. So I hope you will understand. You can take both kind of temperature, like uniform temperature over here, but you also need to take the value of H also a uniform or average heat transfer coefficient. But in the case, if you taken this Ts, or sorry, T infinity value over here, so you also need to take H value, the local H value of a local heat transfer coefficient. There will be different kind of values. So okay, let's lecture 19 is, we end lecture 19 over here. In the lecture 20 we start with the numerical, and I hope it will clear your I hope I will explain all convection. So till then, Hudafiz, we will meet in lecture number 20. Thank you.